Hello Calc 3 and welcome back for another video. In this video we will be covering section 12.1 on three-dimensional coordinate systems. Before we begin our study of calculus with multivariable functions, we're going to need a better understanding of three-dimensional space. So up until this point in calculus, you've only worried about two-dimensional space, functions that you can plot inside of the plane. But we want to move these concepts up to higher dimensions because three-dimensional space is often more useful for real-world problems. But before we can do that, we first need to have a better understanding of three-dimensional space. So in chapter 12, we're going to define the idea of a vector and then vector operations as well, and we're going to use them to study the geometry of space. For those of you who have already taken physics courses, vectors should be quite familiar to you, and at least a good portion of this chapter might be review. So without further ado, let's move on to plotting in three-dimensional space. So to locate points in space, we're going to use three mutually perpendicular coordinate axes. This is analogous to the way that we locate points in the plane. We have an x and a y axis that are perpendicular. In space, or three dimensions, we're going to have our xy plane, but you can think about it as adding a third vertical z-axis, as you can see in the picture here. So now an interesting fact about the coordinate frame we use for space. If you take your right hand, and I actually do encourage you to do this at home, take your right hand and point it in the direction of the x-axis in that picture there. Or point your fingers in the direction of the x-axis. Now I want you to curl your fingers towards the positive y-axis, and if you do that, you're going to find that your thumb is pointing up along the positive z-axis. Because our thumb is pointing along the positive z-axis when we do this, it means that our coordinate frame is a right-handed coordinate frame. If our thumb was pointing in the negative z direction, then we would have a left-handed coordinate frame. You want to make sure that when you're drawing your x, y, and z axes, you're drawing them with the correct orientation so that it's a right-handed coordinate frame. Now, if we're given a point x, y, z, that ordered triplet x, y, z, in Cartesian coordinates, we can plot the point in space by moving along the appropriate axes. Again, this is analogous to the way that we plot points with Cartesian coordinates in the plane. We move a certain distance along the x-axis, and we move a certain distance parallel to the y-axis, either up or down. We'll use the same process to plot points in space. So here are a couple of notes to keep in mind. Points of the form that I have listed here, where two of the numbers in your ordered triplets are 0, are going to be points that lie on the axes. So if I have the point x0, 0, for example, that point will lie on the x-axis. And then you can extend that same concept for the 0y0 point and the 0z point to the y-axis and the z-axis. And we can also consider planes that are formed by the coordinate axes. So the equation z equals 0 will represent all of the points such that the zth component of the ordered triplet is equal to 0. And if you think about it, this is the same as the xy plane. When we have x equals 0, we get the yz plane. And when we have y equals 0, we get the xz plane. And the same way that we split the plane into quadrants with the x and y axis, we can split space into 8 octants with the x, y, and z axis. But unlike the plane, there is not a universal way to number the different octants. All that has been decided on is that octant 1 is going to be the octant where all of the coordinates are greater than or equal to 0. And we should also note that we can define other planes in space that are perpendicular to the coordinate axes with equations that look like x equals some constant, y equals some constant or z equals some constant. And when we do that, we're going to have a plane. So let's talk about specifically the equation x is equal to a. In this case, we're going to have a plane that is perpendicular to the x-axis and crosses through the point a, 0, 0. We can say the same things about y equals a. We would have a plane that is perpendicular to the y-axis that passes through the point 0a, 0 in that case. And analogously, 0, 0a for the third case when z is equal to a. Now for a few examples where we're going to interpret certain conditions geometrically. Assume that we have the conditions z equals 0, x is less than or equal to 0, and y is greater than or equal to 0. We want to find the set of points that satisfies all three of these conditions here. So the fact that z has to equal 0 means that all of the points are going to be in the xy plane, because I know right away that the points are going to have the form xy 0. And the fact that x is less than or equal to 0 and y is greater than or equal to 0 implies that the points are in the second quadrant of the xy plane. Now what if we have the conditions x squared plus y squared is equal to 4 and z is equal to 3? What's the set of points that satisfies these conditions? Well, z equals 3, similar to what we did before z equals 0, implies that the points are in the plane that's perpendicular to the z-axis that passes through the point 0, 0, 3. I think maybe a better way to think about that is taking the xy plane and raising it up to the point z equals 3. That's the plane that we're going to be talking about, so I know my points have to be inside of that plane. And the fact that x squared plus y squared is equal to 4 means that the points have to be on the circle of radius 2 that's centered around the z-axis. And by our first condition, it's also going to be in the plane z equals 3. Finally, for the last section, or subsection I should say, of section 12.1, we're going to talk about distance and spheres. So the distance between 2 points in space is defined by this formula here, or maybe I shouldn't say defined, it's given by that formula there, because we can actually prove it. And a proof of this formula is given in the book. I don't want to go through it here, but if you want to go through it, it is in the book. And let's go through a quick example of finding the distance between 2 points. So we're given the points 2, 2, 2 and 1, 2, 3. We want to find the distance between those 2 points. We just use the formula right above here. So we have the square root of 1 minus 2 squared plus 2 minus 2 squared plus 3 minus 2 squared. And that simplifies to the square root of 1 plus 1, or just the square root of 2. So right after we have a notion of distance in space, we can talk about defining spheres in space. So a sphere of radius r centered at some point, which in this case I'm going to call x naught, y naught, z naught, in space is defined as the set of all points such that the distance from the center to the point is equal to r. So this definition is analogous to the definition of a circle in the plane. It's all of the points that are equidistant from some center point. So if we have a point that's on such a sphere, centered at x naught, y naught, z naught, then the distance from p naught, the center, to some point p that's on the sphere is given by the square root of x minus x naught squared plus y minus y naught squared plus z minus z naught squared. And that has to equal to r, because we assumed that the point P is distance r from P naught. And if we square both sides of that equation, we get that x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to r squared. And this actually gives us an equation for the sphere of radius r centered at x naught, y naught, z naught. Okay, so that's all of the material for section 12.1. Stay tuned for section 12.2.